Hey class, Mr. Mohidian here. Hope everyone got home safe with the storm coming. We're going to take a look at what we would have talked about after our assessment today, and it's beginning the unit on differential equations, our very last topic of new material in calculus. So just to dive right in, what is a differential equation? You're going to get a somewhat disappointing definition. A differential equation is simply an equation involving a derivative. So that is a bit circular of a definition, but as you'll see, it's a useful one for identifying what we can do and what we can't do with differential equations. Speaking of what we can do with them, there's three major topics that we talk about. We're going to talk about the last one here today, but to give you a preview, we're going to be dealing with slope fields, and essentially they're a way to, if there are functions that are difficult to integrate or we don't want to integrate them, or we have no methods to do so, we can use the slope, dy dx, to come up with a solution family indirectly. So we'll see an example of that in just a moment, just a brief picture. Separation of variables is to do it the long way, to be able to take an integral operation and take a differential equation and eventually find the family of solutions, which is the general, and then the particular solution, which is a particular curve. So you can kind of think of those as indefinite and definite integration in a sense. Actually, it's not exactly true, I misspoke there, but they're both indefinite integration. And finally, the one we're actually going to look at is to solve an application, a word problem, essentially, by first translating English into math, figuring out where's the math problem hidden within here, and then using math to answer the question that's being posed, which is often a scientific one. So we're going to look at the first two very briefly for the moment. What is a slope field and what is separation of variables? What do these questions look like? These are both AP questions. So this is a slope field. As you can see, it's an array, it's a field, it's sort of a set of little markings, little gradients you might call these. It almost looks like a weather map, which is appropriate for the reason we don't have school today. These lines, these little segments, have a particular slope, and that slope is defined by, as you'd expect, a particular differential equation. So just as a brief preview of how to do a problem like this, the coordinates of this point, if that's 3, then this would be about 1, 1, right? I believe. So the coordinates there are 1, 1, then x is 1 and y is 1. You've got to figure out which one of these would take 1 and 1 and produce a slope like that, right? And then you take negative 1 comma positive 1, something like this, and figure out, well, what kind of slope do you get there? You should get a negative slope because this is downhill, and only some of these will do that. That way you can figure out which graph, which slope field maps to which derivative, which differential equation. Separation of variables would look something like this. You're given a derivative, and notice in both cases actually y appeared on both sides of, on the other side of the derivative, so to speak. So the function itself is part of the derivative, which is curious. We haven't seen problems like that. So if y equals f of x and dy dx equals x times the original function y cubed, then a question might be posed to find the particular solution to such an equation. So that takes a bit more work, and we'll talk more about those in the future. What we're actually going to look at today is an application problem in the context of differential equations. Before we do that, though, let's review some important log and exponent rules that will be popping up in this particular problem. So the two things you're about to see you've seen before in Algebra 2 or in pre-cal. Log base b of a equals x. If that is true, then how do we do what's called exponentiation? These two statements are equivalent. I'm not changing, I'm not doing any math really. I'm just translating from one representation to another. So to color code this a bit, the base of the log is b, and it is therefore the base of the exponent as well. That's what we call it a base. The log itself is equal to, so the result of a log, this entire quantity, represents an exponent. And the result of that exponentiation is this thing being logged, so to speak. So these are equivalent expressions, and moving freely between one and the other is an important skill to have. So just as a concrete example, if you had ln of e to the third power, the question is, what is that? Well, remember, ln is log base e, and then our a here would be e cubed equals something. Well, translating according to this protocol would say e to the something equals this amount right here, which is a, or e cubed, and quite clearly you can see that the missing number is 3. Again, the exponent is what the log as a total item is equal to. So that's one rule. The other rule that I want to focus on, if I can remember where the invisible rectangle is breaking apart an exponent. So x raised to the a plus b power is equivalent to, again, these are the same thing in two different representations, x to the a times x to the b. So again, as a concrete example, if you want one, if you have forgotten these rules, if you have x to the 3 plus y power, then that's equivalent to x to the third times x to the y. So that's just using this. This is supposed to be that symbol again. These are just equivalent expressions. Okay, so hopefully those seem pretty familiar to you. We haven't seen them in a while, but it's worthwhile revisiting. So what's the actual application problem we're working on today? So let's take a look at the actual problem. Bacteria in a culture are observed to grow at a rate proportional to the number of cells present. At the beginning of an experiment, there are 100 cells present. After 3 hours, there are, as bacteria do, there are now 3,500. There's a lot more. The question is, how many will there be after 24 hours? And when will the original population double? Now, a naive approach to this problem would be to think of it as a linear rate, which is to say, well, you start off at 0, 100, and then you end up with 3, 3,500. But as you can tell, we're not dealing with linear steady growth. We're dealing with, you probably know, exponential growth. But the question is, where in this problem does the exponential actually appear? And what isn't entirely obvious until you do some calculus is that appears in the wording right here. Hidden within this is the idea of exponentiation, or more appropriately, before that, logarithmic behavior. So how do we extract that from this? Well, let's focus on the underlined section here. Bacteria in a culture are observed to grow at a rate proportional to the number of cells present. So as mentioned, we have to translate that into math. So let's set some parameters first. Let's say that B of T, B for bacteria, is equal to the number of cells. You'll also see that periodically as just B. If I say B, that I'm referring to the output, B of T. T, of course, is time. In this case, I believe measured in hours. So bacteria in a culture are observed to grow at a rate. So a rate is cluing us into the idea of a derivative. So what is the derivative of B of T? Well, that would be dB dt, right? Another way of representing that, if you wish, although this way would be a bit better for us, this is equivalent to B prime of T. So dB dt, a rate proportional to, so think back to 7th grade in proportional reasoning. Proportional to means we're dealing with some constant of proportionality. Let me use a more vivid color here. A constant of proportionality, which we normally call K, but proportional to what? Proportional to the number of cells present. Well, the number of cells present is our B of T in the first place. So the rate is in proportion to how many there are at any given time. Which is to say that the more cells you have, the higher the rate. The more cells you have, the faster it's growing. Because if you think about the way bacteria, recreate or procreate, then that's something that's observed in nature as well. So this statement, dB dt is equal to K times B, is a mathematical translation of what I have spelled out here or underlined here up top. The rate in purple, dB dt, is proportional, so is kind of left out here, but equals, proportional is K, proportional to what? Times the number of bacteria present, which is B. So this is our key to this problem, that dB dt is equal to K times B. Now we can do something called separation of variables. We're going to use a procedure involving integration, as we'll get to. So we're going to do what's called separation of variables. It's just a technique here. Let me get rid of this. Is there a rectangle here? There's not. Okay. So let me spell out what I mean by that. Typically, we refer to dB dt as a quantity, as a single unit. So this is a rate, right? We usually use this as a grouping. We don't split this thing apart. We consider it as an entire thing. However, we are going to separate out the dB part from the dt part. We're going to do that by treating this as an equation, which it is, and we use the laws of algebra to allow us to do that. So I'm going to multiply both sides by dt. So dB and dt, which until now usually stay together, we're going to separate those by using algebra, and that gives us dB is equal to k times b times dt. I'm going to group my b's together because they should go together because they're kind of like like terms, although not exactly. And to do that, since this is multiplication, I'm going to divide both sides by b. Now you might think, well, where's the t? I don't have any t's to group together. That's fine. K is just a number, and I'm going to keep it with dt because dt needs something, and b and db have already been grouped together. So I'm going to rewrite this slightly. I'm going to write this as, let's say 1 over b. Oops, ahead of myself. 1 over b times db is equal to, on the other side, we now just have k times dt. So hopefully you're okay with this notation. These are equivalent. What I next do is integrate both sides. Integrate both sides. Once again, it's an equation. I chose to multiply both sides by dt because it was a useful step for me. Likewise, now that I have stuff dB equals stuff dt, I can do whatever I want to, but again, I got to do it to both sides. So what I choose to do is to take the integral of both sides. So I'm going to take the integral here and take the integral there. And now you can probably see why I wrote it like this. Integral of 1 over stuff, d stuff, would just be ln of the absolute value of that stuff plus c. So just some indefinite integration for us. On the other side, remember, k is just a number. It could be 3, could be 1/2, some amount. And dt, well, that would just be a linear function, which would be k times our variable here, t, plus c. So for example, if this was 3, this would be 3t plus c. Normally this is x, but for now it's time t. Remember that c itself is a constant, so if I were to subtract c from both sides, remember these could be different constants, so all I'm getting is a different constant here. So c minus c is still c for reasons that will be spelled out more clearly in class. But for now, it's just an arbitrary number, so it doesn't matter what it is, even when you group them together. So I now have the ln of the absolute value of b is equal to kt plus c. Now, strictly speaking, I don't need the absolute value bars here because what does b represent? B represents the amount of bacteria. And we're not really going to have negative bacteria, so it's always going to be positive. So just to clear that up for us, let's go ahead and erase these bars. It'll make this next step a little bit easier. If you recall from the properties of logs, and I'll bring that back here just for a moment, the properties of log tell us that log base b of an amount is equal to the exponent. So, how can that help us here? Well, let me write ln as log base e, which it is equal to some amount, or some exponent rather. So using the properties of logs, I can then translate this into e to this part, which is kt plus c is equal to b. So how did I go from here to here? I just used log properties. The process here is called, you sometimes hear very fancy, exponentiation is what happened there. And you start to see that we're starting to get an equation for b, right? And from the original, there was no hint of an exponential function, right? This just says dB dt equals k times b, but as a result, we end up with an exponential function. That's curious. Now, this next part also requires properties of logs. Because I'm going to, not of logs, of exponents, excuse me. Properties of exponents, which is to say e to the something plus something is the same, excuse me, as e to the something times e to the second something. We saw this as a and b momentarily a while ago. Okay, now remember, c is a constant. E is a fixed number, 2.718, etc. So e to some number is just some other number. So I'm going to write this whole thing as a different number. I'm going to call it c once again. So c is some number, e to that number is some other number. So what we end up with is c, the c, times e to the kt is equal to b. Remember, b is the number of bacteria present. It's a function of t because the only variable here is t. So we did a lot of work there. Let's look at it in total here. translated from English into math, this color coding, just to give you a sense of what's happening. We then split apart this differential equation by breaking apart dB and dt and splitting them forever, in a sense. And then we grouped together our b's with our db's and our other things with dt. We integrated both sides. We grouped our constants together. We exponentiated. And then finally we simplified a bit to get this thing right here. You'll notice there are two missing parts. Remember, t is a variable, and that needs to be there anyway. We have these two things that eventually need to be replaced. C is something that we need to find a value for, and finding C is something you've heard before. And K also is not a variable. It's a fixed number that we need to find. So how do we do that? That's where the next information comes from. So C equals KT is B of t. The other information we were given was at the beginning of the experiment there are 100 cells present. So let me bring our equation that we just found. B of t, which we were not given, we had to figure it out, the long process, was equal to C e to the kt. And as mentioned, C is something we've got to find, and K is also something we need to find in order to give this a real, a real particularity to it. So we're going to use the information given to do that. There are 100 cells present, so that's the output, that's the number. So there are 100 cells present at the beginning, which is time t equals 0. So you can think of this as this point, or if you prefer, b of 0 is equal to 100. Likewise, after 3 hours, there are 3,500. So b at 3 is equal to 3,500. We have two things to find, and we're given 2 points with which to find them. You could think of this as, 0 equaling 100 and 3 equaling 3,500. What kind of exponential curve models that? That's what we're basically figuring out by using those 2 points. So how do we do that? Step to step. Well, we just use our 2 points to find C and K. So I'm going to use the first one first. I'm going to plug in, I'm going to use the point B, try to keep this color coded, B of 0 is equal to 100. So this is a t value, and this is the output. So B of t I'm going to replace with 100 is equal to C, which we don't know, E, which is fixed, K, we still don't know, times t, which in this case is 0. Oops, 0. So k times 0 is 0. E to the 0, furthermore, is 1. So without too much blood lost, we have C found. So we can now improve this and say, okay, really this is 100 e to the kt. We've already found our C once again. It's 100. We're still missing k. Okay? Well, how do we find k? We'll just use our other point now. So now we're going to use the point b of 3 equaling, so this was from the problem, equaling 3,500. So once again, we plug in this as our output here, 3,500, which is b of t, is equal to c, which we found to be 100, e to the kt. And k is our only variable because t, in this particular instance, is 3, so 3k. So if I divide both sides by 100, I get, let's see, 35, right? Equaling e to the 3k. I need to eventually get k, so I'm going to take the natural log of both sides, because ln e to the 3k is just 3k. ln of 35 is some number, which I'll find in just a moment. To get k by itself, I divide both sides by 3. And thus, that gives me ln of 35 divided by 3 is equal to k, which is approximately, because that's kind of a weird number to work with, 1.185. Okay, pun intended. 1.185. So finally, our equation can be further improved, arguably, by writing this, and apologies for the sound, I forgot to mute it. B of t is equal to 100, which is C, e to the 1.185 t. So this is the particular model of our bacteria culture. Right? This is where it passes through 100 here, and at time t equals 3, it passes through 3,500, not drawn to scale, obviously. So the actual questions were, and I forgot to paste them here, the actual questions were, how many cells are there after 24 hours. So that's, it's basically asking what is B of 24? Well, that's fairly easy. All you got to do is plug 24 into this guy, and you get 100 times e to the 1.185 times 24. And I don't feel like calculating it. In fact, it'll probably be a very large number. After an entire day of growth, you get quite a few bacteria. Actually, I do feel like calculating it now. Sorry for being all capricious. 100 e raised to the 1.185 times 24. Please don't overflow. That's pretty big. 2.2 times 10 to the 14th. Something like that. So we're talking about in the tens of trillions, I believe. Tens of, something like that. Billions, maybe. I have to double check my scientific notation. So there's how many are there after a day. The other question was, how long will it take to double the original population? So that's saying when, which is a time value, what is t such that b of t is equal to, well, the original population was 100, so when is b of t equal to 200? So all you got to do is to set our original equation equal to 200. So b of t, which we want to be 200, is equal to the equation for b of t, which is this right here. And we need to find what this t is. So divide both sides by 100, you get 2 equals e to the 1.185 t. Take the natural log of both sides, so ln of 2 is equal to 1.185 t. Divide both sides by 1.185, and what you get is t is equal to ln of 2 divided by 1.185. Let's give ourselves a number for that. ln of 2 divided by 1.185. The original population doubles in 0.585. So t is equal to approximately 0.585 hours. Remember, time is measured in hours here. So after about half an hour, we've got twice as many bacteria as we started with. And then because the growth rate is proportional to the amount present, the slope increases. And it does so, at a rate which creates an exponential function. So quite a bit of material here. Hopefully you realize this connects derivatives and integration, logs, algebra, all that stuff is at play here. It's a great way to end the course because we're basically summarizing while learning these things. All right, so I'll see you in class on Friday.